In 1835, a 22-year-old engineer named William Otis watched men dig a canal with shovels and wheelbarrows. Hundreds of workers, waist-deep in mud, moving dirt one scoop at a time. The same way humans had moved Earth for 5,000 years. Otis looked at that scene and thought, there has to be a better way. What he built next would move more Earth than every human hand in history combined. It would carve the Panama Canal through a continent. It would reshape the surface of the planet itself. But here's what nobody talks about. The machine Otis invented in 1835 and the excavator sitting on a job site today share almost nothing in common. The excavator went through 3 complete technological revolutions. Each one made the previous machine obsolete. Each one was resisted by the industry for decades. And each one only happened because someone was stubborn enough to prove everyone else wrong. This is the 200-year evolution of the most versatile machine ever built. William Otis was working for the Canton Company in Baltimore when he filed his patent. He called it a crane excavator for excavating and removing earth. The name didn't stick. Workers called it the steam shovel. The machine weighed about 4 tons. It sat on a wooden platform and ran on a coal-fired boiler that had to be fed constantly by a fireman. The boom was made of timber, the bucket could hold about a cubic yard of material, and the whole contraption moved on railroad tracks. Stop and think about what that meant. This machine couldn't move itself. Workers had to lay temporary tracks, shovel the dirt away, then pick up the tracks and relay them a few feet forward. Then do it again. But even with those limitations, the steam shovel changed everything. One Otis steam shovel could do the work of 50 men. That math was irresistible. Railroad companies bought every machine Otis could build. The expanding American rail network created demand for more earth moving than human labor could possibly supply. And steam shovels filled that gap. William Otis died of typhoid fever in 1839. He was 26 years old. He never saw what his invention would become. After Otis died, the steam shovel industry exploded. Dozens of companies started manufacturing their own versions, but one company would come to dominate the era completely. Bucyrus Foundry and Manufacturing Company started building steam shovels in 1882. They merged with Erie Steam Shovel Company in 1927 to form Bucyrus Erie. And for the next 50 years, Bucyrus Erie was synonymous with serious earth moving. Their machines got bigger, much bigger. By 1900, a Bucyrus steam shovel weighed 40 tons and could move 5 cubic yards per scoop. The boilers burned coal at rates that required dedicated supply trains. The operators sat in open cabs, exposed to flying rock, scalding steam, and temperatures that could swing from freezing to 120 degrees, depending on where you were sitting relative to the boiler. Then came the job that would define the steam shovel forever. In 1904, the United States took over construction of the Panama Canal from the French, who had failed spectacularly. The French had tried to dig a sea-level canal and lost 22,000 workers to disease and accidents. They moved millions of cubic yards of earth and still gave up. The Americans had a different plan. They would build locks to raise ships over the mountains, and they would bring industrial firepower the French never imagined. Bucyrus shipped 102 steam shovels to Panama. These weren't the small machines from Otis's era. The largest weighed 95 tons. The bucket could grab 8 cubic yards in a single bite. And they operated around the clock every day for 10 years. The numbers from Panama are almost incomprehensible. American steam shovels moved 232 million cubic yards of earth and rock. That's enough material to bury Manhattan under 13 feet of dirt. The Culebra Cut alone required removing 100 million cubic yards from a mountain range. But there's something those numbers don't capture: the human cost of operating those machines. Steam shovel operators in Panama worked 12-hour shifts in tropical heat. On the boilers radiated temperatures exceeding 150 degrees. The noise from the steam engines was loud enough to cause permanent hearing damage. And the machines themselves were killers. Steam shovels ran on cables and pulleys, controlled by a system of levers and clutches. When cables snapped under tension, they whipped through the air fast enough to cut a man in half. When boilers overpressurized, they exploded. 22 American workers died in steam shovel accidents during the canal construction. Hundreds more were injured. The canal opened in 1914. It was the greatest engineering achievement of the early 20th century, and steam shovels had made it possible. But the steam shovel had a fundamental problem that no amount of engineering could solve. Steam power required water, coal, and constant maintenance. A steam shovel needed a crew of at least 3, an operator, a craneman, and a fireman to keep the boiler running. The machines couldn't travel under their own power, and they were limited in the movements they could make. The solution came from an unlikely place: internal combustion. Diesel engines had been around since the 1890s, but adapting them to heavy equipment took decades. The breakthrough came in the 1920s when manufacturers started replacing steam boilers with diesel engines. Diesel-powered excavators didn't need water, they didn't need a fireman, they could run for hours on a single tank of fuel. And critically, they could be mounted on tracks or wheels that let them move under their own power. But here's the thing. Those early diesel machines still used cables and pulleys to control the bucket. So the mechanical system was exactly the same as the steam shovels. You had drums wound with wire rope, pulleys to redirect the cables, and clutches to control movement. The power source changed, but the fundamental limitation remained. Cable-operated machines could only move in specific ways. The bucket could go up, down, and out. It could curl toward the machine or dump away from it, but it couldn't rotate independently. It couldn't make precise movements. And every single motion required coordinating multiple cables simultaneously. Operating a cable excavator was more like playing an organ than driving a car. The operator controlled up to 8 separate levers, each managing a different cable or drum. Learning to coordinate those movements took years. And even expert operators couldn't make the machine do things the cable system simply didn't allow. The cable era lasted from the 1920s through the 1960s. Companies like Bucyrus Erie, Marion, and Northwest dominated the market. The machines got bigger. A Marion 6360 stripping shovel built in 1965 weighed 14,000 tons and could move 180 cubic yards per scoop. These walking drag lines and power shovels were engineering marvels. But they were dinosaurs waiting for the asteroid. The asteroid came from France. In 1951, a French company called Poquelin built something nobody had seen before, a fully hydraulic excavator. Instead of cables and pulleys, the Poquelin used hydraulic cylinders powered by pressurized oil. The operator moved a joystick, and hydraulic fluid pushed a piston that moved the boom or bucket directly. No cables, no drums. Although no complex coordination of multiple mechanical systems. The implications were revolutionary. Hydraulic cylinders could push or pull with equal force. That meant the bucket could rotate in any direction, at any point in its arc. The operator could make precise movements measured in inches, not feet, and the entire system required just 2 joysticks instead of 8 levers. The first Poquelin hydraulic excavator was tiny by modern standards. It weighed about 15 tons, but it could do things no cable machine could match. It could dig straight down into a trench. It could rotate the bucket to grade a slope. It could work in tight spaces that would strand a cable excavator. American manufacturers looked at hydraulic excavators and dismissed them. The hydraulic systems were prone to leaks. The cylinders couldn't generate the massive forces needed for heavy digging. Cable machines were proven technology. Why change? That dismissal would cost them everything. Japanese manufacturers didn't share the American skepticism. Komatsu and Hitachi started building hydraulic excavators in the 1960s. They focused on reliability and efficiency, fixing the problems that plagued early European designs. By 1970, Japanese hydraulic excavators were outselling cable machines in Asia. American companies finally paid attention when they started losing sales to Japanese imports. Caterpillar, the dominant manufacturer of bulldozers and wheel loaders, didn't even make excavators until 1972. They licensed technology from a German company to rush a hydraulic model to market. No, but the company that truly understood hydraulic excavators was already in Japan. Komatsu had been refining their designs for 15 years, and in 1982, they released the machine that would become the best-selling excavator in history, the Komatsu PC200. The PC200 was a 20-ton hydraulic excavator with a reach of about 32 feet and a bucket capacity of roughly 1 cubic yard. Those specifications weren't revolutionary. What made the PC200 special was everything else. The machine was reliable. Operators could run it for 10,000 hours before major components needed replacement. The hydraulic system was sealed against contamination. The tracks were reinforced to handle rocky terrain. And critically, the machine was designed so a skilled operator could maintain it without specialized tools. Komatsu sold the PC200 for 30 years with continuous improvements. Construction companies bought tens of thousands of them. The machine became the default excavator for mid-sized projects worldwide. But here's what made hydraulic excavators truly dominant. Attachments. A cable excavator could hold exactly one attachment, a bucket. Changing that bucket was a major operation requiring riggers and hours of downtime. The machine did one thing. A hydraulic excavator can hold anything. Modern hydraulic quick couplers let an operator swap attachments in under a minute without leaving the cab. And the list of available attachments is staggering. Standard buckets in sizes from 6 inches to 6 feet, grading buckets for finish work, rock buckets with reinforced teeth, thumbs that turn the bucket into a giant claw, now grapples for handling logs and debris, breakers that hammer concrete with 8,000 pounds of force per blow, shears that cut through steel beams, crushers that reduce concrete to rubble, augers that drill holes 20 feet deep, tilting buckets that can grade at any angle, pile drivers, magnets, vibratory compactors, brush cutters. Count them up and you'll find more than 50 different attachment categories. Each one turns the excavator into a different machine. That versatility is why excavators appear on every job site. One excavator with a library of attachments can do the work that once required a dozen specialized machines. The economics are overwhelming, and the economics keep pushing excavators to evolve. The modern excavator market is a three-way arms race. At the top, manufacturers compete to build the biggest machines on Earth. At the bottom, they race to build the smallest, and in the middle, they fight for every percentage point of efficiency. At the top, the numbers are absurd. Liebherr builds the R9800, an 800-ton excavator designed for mining operations. The bucket holds 47 cubic meters of material. That's enough to fill a typical backyard swimming pool in a single scoop. The machine stands 40 feet tall. It burns 700 gallons of diesel per day. And a single R9800 costs approximately $7 million. Caterpillar's 6090 FS weighs 1,000 tons and can load a 400-ton haul truck in 4 passes. Hitachi builds the EX 8000 series for the Australian iron ore mines. Komatsu's PC 8000 can move 4,000 tons of material per hour in continuous operation. These machines exist because surface mining demands them. Extracting copper, iron, or coal from open pits requires moving mountains of overburden to reach the ore. The bigger the excavator, the faster the material moves, the lower the cost per ton. Mining companies will pay any price for that efficiency advantage. But the fastest growing segment isn't giant excavators, it's mini excavators. A mini excavator weighs under 6 tons. The smallest models weigh barely 1 ton. They can pass through standard doorways, they can work in backyards without destroying the lawn, and they're cheap enough for small contractors to own outright. The Kubota KX040 is the most popular mini excavator in America. It weighs about 4 tons, has a digging depth of 10 feet, and costs around $50,000 new. That price point brought excavators to a market that never had them before. Landscapers, pool contractors, plumbers, and homeowners can now rent or buy machines with capabilities that would have required a full construction crew a generation ago. The mini excavator market exceeds $1 billion annually in North America alone. That growth shows no signs of slowing. And then there's what's coming next. Electric excavators are already in production. Volvo's ECR25 Electric is a 2.5-ton excavator that runs entirely on batteries. It produces 0 emissions and operates at noise levels low enough for indoor use. The battery provides 4 to 5 hours of typical operation on a single charge. The Caterpillar 320 Electric is the first battery-powered excavator in the 20-ton class. It can run a full shift on one charge and recharges overnight. The operating cost is roughly 60% lower than diesel when electricity is cheap. But electricity is just the beginning. Autonomous excavators are in testing at mining sites worldwide. Komatsu has deployed semi-autonomous trucks and excavators at copper mines in Chile. The machines use GPS, laser sensors, and AI to execute digging patterns with precision no human can match. An autonomous excavator doesn't get tired. It doesn't take breaks. It operates 24 hours a day with consistency that maximizes efficiency. Some engineers predict that surface mining will be fully autonomous within 20 years. The technology already works. The only barriers are regulatory approval and the capital cost of upgrading existing fleets. Go back to where we started. William Otis watching men dig a canal with shovels. He built a machine that could do the work of 50 workers. Today, a single Liebherr R9800 can move more earth in 1 hour than 1,000 men could move in a day. That's not an improvement. That's a transformation of what humans can do to the physical world. The excavator evolved from steam to diesel to hydraulics. From cables to cylinders, from single-purpose diggers to multi-attachment platforms that can do anything, from human operators to algorithms that never sleep. Each revolution happened because someone refused to accept that the current way was good enough. William Otis refused to accept manual labor, Poclane refused to accept cables, Komatsu refused to accept anything less than perfect reliability, and somewhere right now, an engineer is looking at today's excavators and thinking the same thing Otis thought in 1835. There has to be a better way. If you want to see how another machine evolved from simple tool to world-changing technology, that video is on your screen now.